So the key word here is press. Okay, so you can see that press and pressure really they're going to die, right? Because blood is life. So we need blood getting to your organs, to your tissues. Otherwise, they're not. But I want to shock you today and let you know that the heart is not the only pump. It's not the only machine that keeps blood moving. The artery actually acts as a pump to also keep blood moving, and I will tell you why. You're welcome to Dr. MiraTeaches, and I will be teaching you hypertension. All right. In this series, we will do blood pressure. Okay, this is the first topic for the series, blood pressure, because you need to know what blood pressure is. And then, based on the understanding of blood pressure, you'll be able to understand what high blood pressure is. Okay, and we know that high blood pressure is hypertension, right? So when you understand blood pressure, then you can understand high blood pressure. Please, it's important that you watch this video to the end so you have the basis and the foundation for hypertension. Okay, so let's get into it by me asking you a question. What would happen if the blood supply to a specific body part were cut off? Right? What will happen if you don't have blood getting to a particular organ or a limb or whatever? What will happen if blood doesn't get to that specific body part? Of course, will result in death of that part of the body because blood is life. Okay, without blood, your organs will die. Right? If blood doesn't get to your organs, they are going to die. So the answer is what? It's death. All right. I'm driving at a point, so just hold on. All right. To ensure that our tissues and organs remain alive, blood is constantly flowing, moving, circulating to be able to reach these organs. That is why you are alive. That's why you're sitting watching this video. It is because blood is constantly flowing. Blood is getting to all the organs in your body. Right. It's just like watering your lawn, your garden, maybe you have potted plants, using a water hose. All right. The tubing that you can use to water your plants, that's a water hose. Okay. If you do not water your plants, they are going to die, isn't it? Because water is life. You need the water to keep your plants looking green and fresh, right? If you don't want your plants to die, what do? You water them, right? Similarly, if you do not water your organs in quotes, all right. So if you don't blood your organs, if you don't blood your organs in quotes, they are gonna die, all right, because blood is life. So we need blood getting to your organs, to your tissues. Otherwise, they are not going to function properly. They will die, all right. And blood gets to your tissues, your organs through a tube. All right, just like you water your plants with a hose, blood also gets to your organs, your tissues through tubes, through hoses. All right, but these are arteries, isn't it? So let's look at the definition of pressure using the Cambridge dictionary. All right. Now, pressure is the force you produce when you press something. So the key word here is press. Okay. So you can see that press and pressure really they are the same thing. Okay. Pressure is derived from the word press. So the force you produce when you press something is pressure. So when you press something, you're applying pressure. So you see, it's not a strange term. The force you produce when you press something is pressure. And we know how we can apply pressure. It's commonly seen when you have a wound and then you would want it to stop bleeding. So you apply pressure, isn't it? You just press. Okay. Now, it can also apply to liquids or gases. So the force that a liquid or gases produces when it presses. So you can apply pressure with your hand, but liquid or gases also are able to apply pressure to an area. All right. So it's still the same word, press. That's a key word. So water, liquid, gas, okay, they press against an area, and that is pressure. All right. So we can have the term gas or water pressure. You see, I didn't say it, it's here in the dictionary, water pressure. So for the English people, this is pressure, and this is the definition of pressure. It's all about pressing against something. The force that you produce when you press something, or the force that a liquid, whether water, all right, or gas, produces when it presses against an area. And usually liquids flow through pipes, isn't it? So when that liquid is pressing against the pipe, you have pressure. If it's water, then we call it water pressure. You see, makes sense, right? But for the physics people, the science nerds, very simple. Pressure is equal to force over area. So it's the force you apply against an area. So you can choose the definition you like. Force over area, very simple. Okay. Or if you're an English person, the force produced when you press against something, or the force produced when water or gas presses against an area. Okay, so that is what pressure is. Depending on the material, the substance you are dealing with, you can give that pressure a name. If it is water, we call it water pressure. And if it is blood, we call it blood pressure. You see, it's very simple. So when blood presses against the arterial walls, as blood moves, it generates pressure, isn't it? Because the blood is pressing against the arterial wall. So blood pressure is the force moving blood exerts on the arterial walls. All right. It is the force that moving blood exerts on the arterial walls. It's very simple, isn't it? So can you spot the difference in this between these two women? Okay, these are two beautiful women holding water hoses, all right? But look at the difference. This water is gushing out, okay, while this is, it's flowing out nicely, but not with a high pressure like this one. Okay, so when water flows at a high pressure, this is what it looks like. And when water flows at a low pressure, this is what it looks like. Imagine the feeling that these two women will have in their hands as they hold the hose. Definitely, it's going to feel more tense in this woman's hand. The hose will feel more tense in this woman's hand as compared to this lady. Okay, it wouldn't feel as tense. The hose wouldn't feel as tense because the water pressure is not that high like this one. The pressure is relatively lower. So it doesn't press as much on the tube or on the hose as this will do. Okay, this will press very hard on the tube, the hose. So she's going to feel it in the hand. So that's what happens when you have a high pressure flow and then you have a low water pressure flow. Okay. Now, this is a twist. When you change the color of the water to red, it becomes blood in it, right? If blood is flowing at a high pressure, it's going to look something like this. And if blood is flowing at a low pressure, it's going to look something like this. But blood is not flowing through water hoses and tubes and pipes. It's flowing through arteries, all right? The arteries are the hoses, the pipes, and the tubes of the human body. Imagine how it will feel if you have an artery in your hand when the pressure is very high. It's going to feel more tense, isn't it? But if the pressure is relatively lower, it's not going to feel as tense as if the pressure was very high. So it's the same analogy, okay? Because remember, whether it's a liquid or a gas, pressure is pressure, and the liquids can vary, whether water or blood, okay? Still the same principle that you can apply. I googled water pressure, as we have seen, and I decided to look at this statement. Low pressure can cause a slow, weak flow of water, while high pressure can potentially damage plumbing and appliances. So low pressure leads to slow, weak flow. You see, so when the pressure is low, the blood tends to flow more slowly and it's not as strong. The flow is a bit weak. Okay, but when the pressure is high, the blood will flow faster and with strength. Okay, so that's the difference between low pressure and high pressure. If the pressure is low, the blood flows very slowly and weakly. It is not that strong. But if the pressure is high, the blood is able to move really fast and you can feel the strength. Okay. Remember this preamble we gave at the beginning, that to ensure that our tissues and organs remain alive, blood is constantly flowing. Blood has to move, blood has to circulate to reach these organs. If blood doesn't get to your organs, the organs are going to die. And God does not want that. We don't want that. We want to be alive and enjoy life. You understand? So blood has to keep moving. All right. But what keeps blood moving? What keeps blood moving? Let's go back to our water analogy. I Googled a water pump, and we know what a water pump does, right? A water pump is a machine used to increase the pressure of water in order to move it from one point to another. So, if you want to get water moving from one point to another, you need a machine that would increase the pressure, and that machine is a pump. And if it's water you are dealing with. It is called a water pump, isn't it? So a water pump is a machine used to increase the pressure of water. So when you increase pressure, what happens? The water is able to move from one point to another. All right. And water is fluid, isn't it? Water is liquid, right? And the same thing applies to blood. So if you want to get blood moving from one point to another, because remember, blood has to keep moving for your organs to remain alive. Blood must circulate, blood must flow, right? So if you need blood to move, what do you use? What do you employ? You need to use a machine, and that machine is a pump. And I'm sure you know what I'm driving at. What pump are we talking about? What machinery are we talking about that keeps blood moving? I know what you're going to say. You're going to say the heart, right? Yes, it is the heart. But I want to shock you today and let you know that the heart is not the only pump, it's not the only machine that keeps blood moving. The artery actually acts as a pump to also keep blood moving. And I will tell you why. Now, the heart pumps, okay, and then relaxes, isn't it? It pumps and then relaxes. It pumps and then relaxes. It is not always pumping. Okay, it's just like a water pump. You can turn the water pump on and then you turn it off. You turn the water pump on, then you turn it off. Once the pump is on, the water is able to move. Okay, the same way for the heart. Once the heart pumps, it contracts, blood is able to move. But then the heart doesn't always pump. The heart goes on and off, on and off, on and off, pump, relax, pump, relax. That's what happens. So when the heart relaxes, how does blood move? How do we get blood to move? The artery takes over. All right. The artery takes over. It shock you. It shock you. It shouldn't. All right. It shouldn't shock you. Remember, we need blood to keep moving for our organs to be alive. And we have and we need a pump so that blood can move from one point to another. We need a pump, we need a machine, all right? That machine, that pump is the heart, okay? But the heart is not always pumping. It pumps and stops, it pumps and stops, it pumps and stops. It pumps, okay? It contracts and then it relaxes. It contracts and then it relaxes. So when it contracts, blood is able to move. But when it relaxes, blood isn't moving, isn't it? So the artery will take over the point where the heart isn't pumping. All right. Yes, that's what happens. And I will show you in this image. Now look at this. The heart pumps, right? It contracts. Once the heart pumps, blood flows with a high pressure. And the arteries, right, they expand because the arteries are elastic. They are elastic. They are like a rubber band. Okay, you can stretch it, right? They are elastic. So once the heart pumps, the blood moves with a high pressure, and because the arteries are elastic, they actually stretch. You get it because of the high pressure. So that's how blood moves when the heart pumps. But God wants our blood to constantly flow so that our organs don't die. So when the heart relaxes, how does blood continue to move? All right. The arteries act as a pump, okay, through the action of what we call the elastic recoil. Because the artery is elastic. When the heart pumps, the artery expands, okay. But when the heart relaxes, to keep blood moving, the arteries snap back, okay. They snap back to their original shape. And that force they produce while snapping back keeps the blood moving even when the heart isn't pumping. Do you see? It's very interesting. And I think God is wonderful for doing that. Do you understand? So the heart pumps, okay, in systole, the blood moves with a high pressure, lets the artery, expand. Okay, the artery is able to dilate, okay, because it's elastic. But then once it stops pumping and relaxes so that it can fill, the arteries will snap back. It's like a rubber band. You stretch, when you release, it snaps back. That snapping back action helps the artery to return to its original shape and also to keep the blood moving. So whether in systole or in diastole, blood is moving, but the pumps, the machinery that keeps blood moving are different. In systole, it is the heart that keeps blood moving, but in diastole, it is the elastic recoil action of the artery that keeps blood moving. So you don't die in diastole. Your organs wouldn't die in diastole. All right. Systole, diastole, blood is constantly moving. Isn't it wonderful? All right. So that's what happens. And that is why when you feel the pulse, okay, when you feel the pulse, during the systolic phase, all right, or when the heart beats, okay, you feel the expansion beneath your fingers. You are able to feel that expansion. But then when the heart relaxes, okay, and the elastic recoil takes over, you no longer feel the the artery beneath your fingers. Okay, so that's why you are able to feel the pulse as beats because it contracts, the artery expands. Then when the heart relaxes, the artery undergoes elastic recoil, so you no longer feel it under your fingers. Okay, so that's how we feel the pulse. All right. So all I have said is that when one pump stops, the other takes over. This is to keep the blood moving. Okay, so the heart pumps in systole, and then the artery's elastic recoil will pump in diastole. Like, do you get it? Yeah, you only get this on Dr. Mira Teaches. Okay, so what are you waiting for? Please like, share, subscribe. Okay, so blood is always moving, it's always moving, it's always moving. You need a machine to keep blood moving. Everybody will say, oh, yes, it is a pump, isn't it? Just like water has to move from one point to another, you need a water pump. The same way you need a blood pump. Everybody knows that the heart keeps the blood moving, right? The heart pumps so that blood moves. But then the heart is not always pumping. The heart pumps and relaxes. It pumps and relaxes. In its relaxing phase, that is in diastole, blood has to keep moving because your organs have to remain alive. And what keeps the blood moving is your artery's elastic recoil. So once the artery snaps back into its original shape, it's able to produce a force that keeps water. Sorry, we are talking about blood. That keeps blood moving, you know, within your arteries. Okay. Now, I want you to note this distinction. Remember, blood has to always move. Blood must always move. Okay. And we need machines to keep blood moving. And these machines are the heart and the artery, right? But one machine is stronger than the other. The heart is a stronger machine, is a stronger pump as compared to the artery. All right. So the heart pumps with a stronger force. All right. Because it pumps with a stronger force, blood will move with a higher pressure in systole. All right. However, when the heart relaxes and the elastic recoil takes over as the pump, you know, the force that it generates is lower. The artery's elastic recoil can't be compared to the strength or the force produced by the heart pumping. So the blood will move with a lower pressure in diastole. All right. So the point is that blood is always flowing, but at different pressures because different machines are acting at different times. Different pumps are acting at different times. When the heart contracts, blood moves with a higher pressure. And when it relaxes, the elastic recoil action takes over as the pump to keep blood moving. But it is not as strong as the heart, you see. So the blood moves at a lower pressure. So at every point in time, blood is flowing, just that the pressures at which blood is flowing is different. So this is your secret sauce that you must understand. Once you're able to understand this, you can understand hypertension. All right, where are you going to get this kind of information? But on Dr. Mira Teaches. So please like, share, and subscribe. All right. Now, that is why when you check blood pressure, all right, you notice that the top value, which is your systolic blood pressure, is always higher than the lower value. Do you see? Because the heart is stronger than the elastic recoil action, you know, that goes on, all right, to keep blood moving. All right. The heart is very strong. So in systole, if you have a BP of 115 on 65 millimeters of mercury, in systole, blood will move at a pressure of 115 because the heart pumped with a higher pressure. However, when elastic recoil takes over in diastole, that force is not as strong as the heart. So the pressure at which the blood moves is lower, right? And it will be 65 millimeters of mercury. So it's making sense, right? It's making sense. So that is why anytime you measure blood pressure, the top value is higher than the bottom value. The higher value represents the force. It represents the fact that it was the heart that acted as the pump, all right, in systole. However, the lower value tells you that the moment the heart relaxed, the moment the heart stopped pumping, the elastic recoil took over. However, it has a lower strength. It is not as strong as the heart. So the pressure during that time was lower. I hope it's making sense. Okay, now if we wanted to measure the pressure of water flowing through a pipe, all right, what instrument do we use? We use a manometer. I didn't say so. I took this image from a site online, a research site online. We are not doing plumbing, all right? But then it says that the first manometer measures the water pressure in the pipe before passing through the fiberglass, blah, blah, blah. All right. So we are looking at the fact that it is a manometer that measures the water pressure in the pipe. Look at this image as well. It says the second manometer serves to measure the water pressure in the pipe after passing through the fiberglass, blah, 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 blah tube. All right. So I just want to drive home a point that if you want to measure the pressure at which water is flowing, there is an instrument, there is a device that we use, and that is called a manometer. You see where I'm going? I know you see it. Okay. Look at this tube, look at this hose, right? To measure the pressure of water, sorry, pressure of water passing through this hose or tube, you need a manometer, isn't it? Similarly, if you want to measure the pressure of blood passing through the brachial artery, you will use a manometer as well, but this time it is a sphygmomanometer. All right, so it also measures the pressure of blood in the pipes. All right, that is the arteries. Okay, so it's not rocket science. It's not being conjured from the skies. Same instruments. All right, there may be slight differences in the names. Okay, so you have an assignment to go and find out what sphygmo means. All right, it has a meaning and it applies to blood. All right, okay, so sphygmomanometer measures the pressure at which blood is flowing in the pipes being the arteries. All right. Isn't it fun? Yeah, I know, right? I can see the smile on your face. Yeah, I see you. I see you. Okay, so when you're measuring somebody's BP, whether you're a nurse, doctor, whatever, as you put the cuff around, just remember that it's just like a manometer, all right? It's the same thing. You're measuring the pressure at which the blood is moving within the artery, specifically the brachial artery, right? This bonus slide is on mean arterial pressure. You may have heard of it or you may not have. Okay, but I'm just here to make it simpler for you to understand. So, just like the name, mean arterial pressure is just a mean or average, all right? Mean or average. In math, when you had to calculate the mean or average of two numbers, you add the numbers and divide by two, isn't it? If there were three, you add the numbers, divide by three, right? Okay, so mean arterial pressure is just the mean or average of your systolic and your diastolic arterial pressures. However, there is a twist. You don't calculate it like your regular mean. So just stick with me. I'll get to why that is so. So it is more accurate, all right, and a better marker of blood flow to vital organs. That's why it's important to talk about the mean arterial pressure. It is more accurate as compared to just using your regular BPs. All right, it's more accurate, it's a better marker. It tells us that we have enough blood getting to our organs or tissues. And the normal range is between 70 to 100 millimeters of mercury. That's your normal MAP. All right, this is where we want our pressures, to fall within this range. Okay, we don't want it to go below 60 millimeters of mercury. Why? You need at least 60 to keep your organs functioning and alive. So anything less than 60 millimeters of mercury for your MAP and your organs will die. Okay, there will be ischemia and eventually infarction. So we do not want that. All right. Okay, so why is it that this isn't your regular mean or average? Why can't we just add your systolic and your diastolic arterial pressures and divide by two? Rather, it has this weird looking formula. The reason is because the diastolic phase is longer than your systolic phase. Do you see? You want your heart to have enough time to fill with blood, to relax and fill with blood. That is why the diastolic phase is longer. So that's why the formula looks a bit complex. It isn't complex really. It's not complex. It just accounts for the fact that the heart spends more time in diastole. All right. So that's why it looks this way, and you can't just divide it by two. Okay. So what's the formula? Mean arterial pressure is equal to diastolic blood pressure plus one third of your pulse pressure. Very simple. Diastolic blood pressure plus one third of your pulse pressure. What is pulse pressure? Pulse pressure is just your systolic blood pressure minus your diastolic blood pressure. Okay, that will give you pulse pressure. So this is it. Then we have another formula. All right, it's equal to mean arterial pressure is equal to your systolic blood pressure plus two times your diastolic blood pressure divided by 3. Okay, so you can choose any of the formulae. Okay, and you can experiment. You can write your own BP, use any of the formulae, or use both formulae. You realize that you get the same answer. All right. So thank you for sticking till the end. I hope it was helpful. Please like, share, subscribe. Okay. Thank you so much. Have a good day, good night, good morning, whatever time you're watching this. Plenty hugs and kisses. Bye bye.